So now we're going to be looking at some more conservation of energy principles, but we're going to be looking at it in conjunction with potential energy. So how much gravitational potential energy is stored in the Great Pyramid of Cheops, given that its mass is about that and its center of mass is 36.5 meters above the surrounding ground? So potential energy, or gravitational potential energy, is mgh. This assumption is when you're close to the surface of the Earth. So you can't use this when you start getting when you're using like universal law of gravity. When you're like the moon's potential energy is not equal to this relative to the Earth. So you'd be careful when you use this equation. But most of these kinds of problems are typically like close to the surface of the Earth. You know, it's fine. So we would do the mass 7 times 10 to the 9 times 9.8 times the height, which is 36.5. The height is always to the center of mass. And that's 2.5 times 10 to the 12, and the units of energy are joules. So that's joules. And then how does this energy compare with the daily food? Actually, ignore that part. I mean, it's a lot of energy. A camera weighing 10 newtons falls from a small drone hovering 20 meters overhead and enters free fall. Okay, so we have a little drone here, and it dropped a little camera. This height is 20 meters. What is the gravitational potential energy change of the camera that drone to the ground if you take the reference point A to the ground being 0 gravitational potential energy? So to say that this is 0 gravitational potential energy is just say this is H is equal to 0. So when I do mgh, so for part A, when I do mgh, I simply do, well, mg is 10 newtons times the height, which is 20 meters, and that is 200 joules. Now, what is the change? It was at 200 joules, and now it goes to 0. So up here, it has 200 joules of potential energy. Down here, it has 0. The potential energy equals 0, so the change in the potential energy is the final, which is 0 minus 200. It's negative 200 joules. Okay. B, the drone being 0 gravitational potential energy. So here we're going to say H is equal to 0. What is the gravitational potential energy camera before it falls from the drone and after the camera lands on the ground? Okay. So for B, what is the gravitational potential camera before it falls from the drone and after? Okay, so it's really C and D. Before it falls from the drone, it's at 0. Because if we're going to say H is 0, then the PE up here would be mgh. And then we're saying this is H equals 0. So this is 0 joules. Now for D, we're going to say PE is equal to mgh. But we have to be careful on the M and G and the H terms. Now, the H is going to go to negative 20 meters. And so the way you would think about it is this is the, you would just, because it's downward, it's below. So basically when you're closer to the center, like when you're doing height, upward always has to be positive when you're doing potential energy. Not when you're doing height. When you're doing potential energy, upward always has to be positive. Because that's just how the formula works. The further away you are from the Earth is more potential energy, and the closer you are to the center of the Earth is lower potential energy. So this has to be negative 20 meters here. So that's 10 newtons times negative 20 meters, or that's negative 200 joules. So the change in the potential energy is going to be the same still, because you're going to do its energy down here, which is negative 200 joules, minus 0 joules. The change in potential energy is still negative 200 joules. Okay, so even though the potential energy is different at different point, depending on the reference point, the change in potential energy is always the same. Okay, after the camera lands, what is the gravity of the camera before it falls from hits from the drone? That's 0. And D, after the camera lands on the ground, if the reference point of 0 gravitational potential is taken a second person looking out of the building 30 meters from the ground. So if someone else was out here and we said 30 meters and we said this was the 0, H equals 0, then the change, then this this potential energy, when it is negative 30, so you would say for D, the potential energy is mgh, and that's equal to 10 newtons times negative 30, which is equal to negative 300 joules. And the reason it's 30 is because the ground is 30 meters away from here, right? So, okay, in a downhill ski race, surprisingly little advantage is gained by getting a running start. This is because the initial kinetic energy is small compared with the gain in gravitational potential energy on even small hills. To demonstrate this, find the final speed and the time taken for a skier who skis 70 meters along a 30-degree slope neglecting friction. A, starting from rest. Oh, okay. So we have someone who is going down this 30-degree slope. And I'm just going to put him here, and he's moving. Okay. And so if we want to compare from up here to down here, we want to say, well, what is... You could do kinematics for this. You could do a free body diagram, find the acceleration, and then, you know, like, I don't know if you remember from kinematics, A is equal to G sine theta. You could use that and use our kinematic equations to solve for this. Or you can use energy. So initially, how much energy he has is only potential energy. He only has mgh. Okay, and all of that potential energy gets converted into kinetic energy if we say that down at the bottom is h equals 0. Okay, because then we would say then it has no potential energy down here. It may start with some kinetic energy, but for part A, it doesn't start with any kinetic energy because you're starting from rest. So we don't have any kinetic energy. So mgh is going to be... Oh, he's going to ski down 70 meters. Actually, maybe we won't do energy. Maybe, no, we'll do it with energy. This is an energy unit, so we'll do it in terms of energy. Okay, so we're going to travel this distance 70 meters. I need to know what the height is, though, that I started at. Well, if I know this is 30 degrees, I know that the, let's see, what is it? The sine of 30 degrees is going to be h over 70, right? Opposite over hypotenuse. So h is equal to 70 sine 30. Kind of like when we do angles, is the opposite side, so it's hypotenuse times sine of 30. Okay, so that's the energy. So this mgh is equal to 1/2 mv squared. Turns out the mass doesn't cancel. The velocity is just going to be the square root of 2gh. And that's the square root of 2 times 9.8 times 70 times sine of 30 degrees. Okay. 2 times 9.8 plus 70 times sine of 30 degrees. That's like 1/2, I think. Sine of 30? Yeah, 1/2. 7.4 meters per second. And then B, saying he starts with some energy. So now we're going to say he starts with some energy. V naught squared. Just to be clear. Okay, again, the m's will cancel. But now VF is going to be the square root of, I multiply by 2, I'm going to have V naught squared plus 2GH. And I don't know if you recognize this. This is just like our kinematic equations, right? So it's going to be 2.5 squared plus 2 times 9.8 times 70 sine 30 degrees. Okay. 2.5 squared plus, and I get 7.80 meters per second. So basically, very small difference in speed. Even though they started off with a 2.5 meters per second difference, it caught up. It was a point only. It ended with a 0.4 meters per second difference by the time it's the bottom of the hill. It's still when it's, but you know that 0.4, you know, for gold medal events or Olympics or something like that, like, you know, that difference matters. But you know, like in a casual, like you're gonna race your friend down, it's not gonna make that big of a difference. Thanks for watching. If you enjoyed this video, I go through a lot more of these exact kinds of problems with much longer videos on my website. It's entirely free. Check out the link in the description below.